Good afternoon, and welcome to the Device 2 session, session 4 of the Non-Volatile Memory Workshop. I'm Janice, the session chair, and I'd just like to take a moment to take this opportunity to show we have a position at HP Labs opening up. And if you go to jobs.hp.com and put in that number, when it says search for a job, 560408, you can get more information on that and apply online if you'd like to. But I'd like to introduce our first speaker. We have, actually I'm on the wrong page, Subho Chatterjee is going to talk on energy efficient circuit system co-design for spin torque transfer random access memory in Submicron Technologies. Thank you.
Good afternoon, everybody. So I am Subho Chatterjee from the Georgia Institute of Technology, and I'll be presenting my work on energy efficient circuit system co-design for STT-RAM in Submicron Technologies. So thanks to NVMW for allowing me to present my work. And our work has been a collaboration between the Green Lab at Georgia Tech, to which I'm affiliated, Castle and at Georgia Tech, and the Nanoscape Lab at Case Western Reserve University. So let me move on to the first slide. Actually, since morning, it's been kind of stated and restated about the operations of spin torque transfer RAM. So I'd just like to briefly go through this because by this time, almost everybody knows it. So the storage element involved is MTJ, or the magnetic tunneling junction. And then you have this spin polarization of the electrons that leads to the parallel or the anti-parallel configuration with respect to the fixed layer. And these are some of the advantages of using STT-RAM. Challenges are, as has been mentioned, the high switching current and the issue of bidirectional switching. So let's move on and identify some of the read and write issues that we have and what are the metrics that we have in order to quantify them. So in order to write, I must have the write current to be greater than the switching current, and the amount by which the mean write current is greater than the switching current is what is quantified by the write margin. Similarly, in terms of read, we have the read margin, which is the difference between the mean read current and the switching current. And then we, for the sensing requirements, we have to have the current difference between the 0 and 1 currents, as is shown in the leftmost figure, to be of the order of the offset of the sense amp. Otherwise, if it's less, it leads to sensing errors. And depending upon specifications, the read current might be 3x lower than the write current. So the basic purpose is that now that we have these figures, let's understand what goes on to happen. So if the write current increases much, that is, we try to improve upon the write margin, what we might end up doing is expending a higher amount of energy. On the other hand, if we try to push the read margin to be larger in order to avoid read disturbs, we might actually run into this domain of read errors where the sensing accuracy might become quite an issue. So all these phenomena, all these metrics are intertied, and they have their own impacts towards energy efficient cell design as well as the system design with STT-RAM. So my background has been circuit, so I'll try to look at it from the circuit perspective, and we also have been collaborating on the system front, so we will also try to understand some of the system implications of this as well. So having talked about the STT-RAM matrix, let's see how it maps. So if we try to pictorially represent it, what we have is, first of all, we have the write margin. So of course, the write current has to be greater than a given amount of current in order to fall into the acceptance region. If it falls below, it goes into the rejection region. Similarly, we have the read margin and the current dictated by the read margin. So if the current is greater than the one dictated by the read margin, it could lead to read disturb. So it's a reject in that direction. It's an accept for cases where we have the current lower than that. And again, we talked about sensing reliability. So sensing reliability is yet another metric, and based on that, we have another acceptance and rejection region. So depending upon the design specifications that we might have for a particular cell or STT-RAM array, we kind of hit upon a final solution space, so to say. And the final solution space is shown by the intersection of these curves towards the leftmost part. And if we evaluate the energy within this final solution region, what we find is there will be these different energy solutions as we traverse this space. So there is what we call an optimal energy point for an energy efficient design. The property that we would like to stress upon is that this optimal energy point, so-called optimal energy point within the final solution region, will depend upon the read-write characteristics. That is, what amount of read or what amount of write we are going to use for that particular application. What we see is that for most of cases where the write probability is of considerable magnitude, the write energy by far dominates the read energy. And this is expected because the write current is expected to be like almost, as I stated, in cases 3x or more higher than the read current. So the question we have is, could we think of some circuit and architectural combined techniques to bias the cell and system design so that it becomes a much more energy efficient operation? So in order to do that, as we understand from this figure, the basic thing that we might require is some pre-knowledge or preconceived knowledge about how the read or write skews are for a given application. So here is kind of a framework that we have been using. So first of all, we have the performance constraints and the application characteristics coming in. By application characteristics, I mean the read-write ratios that we have for a particular application maybe. And the performance constraints are the cell design space constraints that I had shown earlier in the diagram. So depending upon that, we perform a design space exploration to hit upon the energy, permissible energy region. And then we did some work along developing a simplified energy model for the STT-RAM array. And we used the energy model in order to evaluate across the design space in order to find out the energy optimal point. So once we have an energy optimal cell for a given application characteristic and a set of performance constraints, the next question we have is, can we do more? So that is yet another level where we go on mostly in the system domain. And we try to answer this by understanding what exact application the array is used for, and hence we apply some energy reduction methods at the system level. So for example, if it's used in case of LLC, as we will show later, we use some mechanism called write biasing in order to have greater energy savings across the STT-RAM array. If it's for read-intensive case, such as memory-based computing, again, I'll come to that later, we have another technique called the preferential mapping to achieve the same goal. So the point I want to hit upon in this slide is that, first of all, we have a framework for the energy optimal cell design, depending upon the application characteristic and the performance constraints. And then once we have this cell, we actually go on to realize what application is it going to be used for, and accordingly apply suitable energy reduction methods for the system. So this is a simple diagram which goes on to show that if we run across different applications, they will essentially have different read-write ratios. And not only that, within an application, the read-write ratios will depend upon the cache design parameters. So what does that imply for STT-RAM? So if we have a prior knowledge about the ratio, then we can actually orient the design to have significant energy savings. So if we look at the diagram towards the left, what we see is it's being the cell that's the best case comparison is designed at a write probability of 0.5. And as the write probability reduces in this zone, and these are cases which are read intensive, my percent savings in energy increases because these have been optimized for a low write probability. So the point is that if we can somehow have a good estimate of the write and the read probability of this application, then we can accordingly modify our cell design in order to achieve a better energy efficient cell. So what happens if we try to map STT-RAM into an LLC cell? So replacing SRAM by L2 and LLC caches by equivalent size STT-RAM, we can see that, of course, there's a huge decrease in leakage energy. And this is quite expected because it's essentially a non-volatile solution. But there's also a corresponding 39% increment in the dynamic energy of the L2 plus LLC cache. And yet again, oh, sure. And this is yet again expected because because STT-RAM, as we stated, is write energy intensive. So what kind of architectural optimizations can we have? And this is a work that we had in ISLPD 2010. And the optimizations that we were thinking of, first of all, we were seeing that if we try to replace the SRAM, the existing conventional SRAM, by an STT-RAM cache of similar size. So what happens is, of course, there is a higher dynamic energy hit and latency, but because the cache area is lower and the leakage goes down significantly. Next, we resort to something else. We see that because STT-RAM has a condensed area, so for the same area, can we fit in more amount of memory? So that is what we call as the constant area analysis, and we find that we finally hit upon a lower execution time because now the memory, the cache size is higher, but we eventually have a higher dynamic energy as well. So I'll actually not talk about these techniques, but the techniques that we adopted, the write biasing and write cache, you can actually look at the paper in order to get about the details of the technique, but it's something to do with the reduction of dynamic energy of STT-RAM LLC by actually controlling the amount of write accesses to the LLC. And this is required because STT-RAM is, again, a write energy intensive operation. The second example I'll come across is that of a reconfigurable computing platform, and it's a read-heavy scenario because in this scenario, what we do is we try to write to it once and we read from it multiple times. So what is the memory-based computing scenario? So it's a computing platform where function response is stored in a lookup table, and we have a lookup-based evaluation performed by a CMOS controller. So as we can understand that we try to map the function response into this 2D memory array, which is realized using the STT-RAM. And as we do multiple, and for one write that we perform to this array, we do multiple lookups based on the CMOS controller. So obviously, my cell design should be based towards the case of a high read probability, because that is what is going to be going to give me an energy advantage over the equiprobable counterpart. So understanding the nature of this particular scenario, we can actually bias our cell design towards optimizing it for a higher read probability. But we also note here that, so the next question we have is, can we do more? So the observation we make at this point is a read 0 actually goes on to consume a higher power compared to a read 1. And this is for obvious reasons that the resistance states are pretty much different. So what we try to do is we try to perform what we call a preferential mapping so as to increase the amount of logic ones that we have for this application, so that at the point of access, we go on to access once more and rather than zeros, and thereby we have some energy savings. So this is a set of results that we presented at the Nano conference. And what we realized is that, so as I speak about it, we have two levels of optimizations. First of all, the cell has been designed towards a higher read probability, and that in itself saves a certain amount of energy. And next, we perform a preferential one mapping in order to bring about some further savings in terms of energy. So it's essentially what we call a circuit architecture co-design, because the first step is a circuit step, and the second step is based on like the system architecture. So what we observe really is with application of the optimization A, that is designing a cell for a higher read probability, the delay actually goes down. In fact, the delay of this memory-based computing is expected to be less than FPGA, the equivalent FPGA models, irrespective of the application. But with the application of the cell design for high read, we note that we have a decrement of 5% in EDP by using MBC. That's good. Now, with using A and B both, that is, first of all, designing the cell for that particular read ratio and read to write ratio, and then applying some kind of a preferential one mapping, we actually can go on to increase this savings from 5% to 6.64%. So the point is that we can actually design the cell such that it has a lower amount of energy in comparison to the equiprobable case. And then with that cell design, if we go on to apply system level solutions, understanding the nature of the application, we can reap even higher energy benefits. So that concludes my talk. So STT-RAM in itself is an exciting new opportunity and brings about a lot of new challenges. So one of the challenges is the inherent skew in the read and write, and is critical for the design. Now, how do we overcome this skew? We can acknowledge this skew and co-analysis and perform co-analysis and co-design, keeping in mind the circuit and architecture level properties of the cell and the application for which the cell is being considered, and that in itself will lead to greater amount of energy benefits as we move across with the application of this new technology. So thank you, and these are some of the relevant publications, the results of which I have used towards this talk. Thank you all once again, and I'd like to face any questions you might have.
The right biasing technique you mentioned in ISOPAD 2010.
Yeah.
Right cache.
Yeah. So actually, the part I am involved in is the circuit part of the design, and to what extent would you like to bias the writes and the reads in order to achieve energy benefits? So I can, tell you this much, that it involves some kind of, so we were like using, trying to use STT-RAM LLCs, and we had this cache by means of which we were like trying to filter out some of the writes which were going into the STT-RAM LLC. Now that involved some other techniques as well, which had to do with the kind of policies you would adopt for eviction and all that. But I guess like you could actually have a look at the paper, so it discusses all of that in detail.
Thanks.
Thank you.
Are there any other questions?
Thank you.
Next, we have Anurag Nigam speaking on model-based study on performance and energy optimization for STT-RAM.
Hello everyone. Thanks for skipping another talk and coming to this session. I am Anurag Nigam, and this work is done in collaboration with Kamaram, Avik, Stuart, and my advisor Mircea. So today we had like almost 3 talks on STT-RAM. So mostly I will talk about the modeling part of STT-RAM bit cell, and then using that model we propose couple of energy reduction techniques. So here's the outline of my talk. First I will talk about the motivation of this work, then quickly glance through the bit cell, STT-RAM bit cell overview. Then in detail I will talk about the self-consistent model of magnetic tunnel junction, then results on the model validation, then using this model how to reduce the challenging issue of STT-RAM, the write energy. So this table was presented to like 2 years back in a flash memory summit that compares the STT-RAM, ReRAM, phase change RAM with the existing memory technologies. So here we can see that if you compare STT-RAM with for different metrics, we can see that it gives comparable read-write time to SRAM. It has a high endurance greater than 10 to the 15, and due to non-volatility, it doesn't consume power. It doesn't have a leakage power, and it has due to one transistor bit cell, it has a density comparable to DRAM. So yesterday in that tutorial we had a question like whether PCRAM is the best option for the main memory or not. So I think that if you are not targeting for L1 cache, so STT-RAM is probably the best for all the different memory hierarchy levels. So now why do we need a physical circuit model for the MTJ? So STT-RAM is still an emerging memory technology. So lots of device researchers, circuit designers are working on it. So as a device designer, we need to study the effect of different material properties on the energy and performance of STT-RAM. And as a circuit designer, we need to integrate the full memory array with the peripheral blocks and then compare its performance with the existing memory technologies. So for both of these purposes, we need a circuit model, and that should be physics based. So that's what we have. I will talk about. So I will quickly go through the bit cell overview. So bit cell consists of one transistor and an MTJ, and the MTJ has two ferrometric layers, and the information is stored in the form of relative orientation of the magnetization. And when the two magnetization are oriented in parallel direction, we have a low resistance state called RP, and when they are anti-parallel, it's high resistance state. Now, in our model, we have the modeling of the magnetic tunnel junction, we have captured 3 different aspects. One is transport part that basically calculates the DC characteristics, how much current will be flowing if you apply a given voltage. The transient part calculates the switching speed, how much time it will take for MTJ to switch from one state to another. And the thermal part calculates, so basically it captures the intrinsic variation of MTJ. And all these blocks are correlated, like transport parts provides a spin polarized current that is taken as an input in transient part, and the transport part provides a current due to Joule heating that increases the temperature, which is taken as an input into the thermal part. Now once we have this MTJ model, we can just connect in series with an MOS to get a bit cell of STT-RAM. Now the transport model, so this figure shows the energy diagram of the MTJ. We have 2 ferrometric layers, and in between there is a oxide barrier. So when we apply voltage across this MTJ structure, so the energetic electrons tunnels through this barrier to the other ferromagnetic layers. And to calculate the current for a given voltage, it will depend on this equation. It will be the addition of the transmission probability over the available states in this ferromagnetic layer. And this transmission probability will depend on the orientation of the spin. So to calculate the density of state, And to calculate the spin-dependent transmission probability, we have used a simplified parabolic EK band diagram for the density of states in the ferromagnetic layer. So the top parabola is for the spin down states, and the down parabola is for the spin up states. And the density of states can be calculated using this equation. Now for the parallel state, the transmission probability is the summation of up spin and the down spin. And similarly, in the anti-parallel state, it's the summation of up down spin and the down up spin. So now, when we put this the transmission probability into the equation and add it over the available states, we get a numerical equation. But if we want to implement that in a SPICE model, we need an analytical version. So we have simplified that equation, and we have introduced two fitting parameters: the effective mass of electron and the delta, the band splitting between spin up and spin down bands, to get an analytical equation. And other thing is that in the experimental RV plot of MTJ, we observe a sharp peak at 0 volt. So we have included a modulus sign in our analytical version to capture that peak also. So this result basically compares the numerical versus analytical expression that we have simplified to implement in a SPICE model. So the left figure shows that if we use same effective mass, so there is a large error in the red curve is the numerical, and the blue curve is the analytical version. So there is a large error, around 17% in the analytical version of the current. Now, if we use this M as a fitting parameter and decrease M for the analytical version, we can almost get close to the numerical expression, the numerical version of the current. So we have used M and delta as a fitting parameter to get a simplified analytical equation. Now, after getting that, we have used behavioral current source in the SPICE model to implement the transport part. Now, the transient part basically calculates how fast your free layer switches from one state to another. So this figure shows the free ferromagnetic layer, and so it depends. The switching time depends on how fast your magnetization vector switches from one state to another. So there are several torques that acts on this the magnetization vector, like uniaxial and anisotropy torque, spin torque. So all these torques are taken into account in the LLG equation, and that the solution of that equation gives the variation of this the free layer magnetization vector as a function of time. And in our model, we have separately included both the in-plane MTJ and the perpendicular MTJ cases. Now we get this LLG differential equation which has these torques as input. Now to implement this differential equation in SPICE, so we have made a conversion. So the free layer vector is represented as a theta and phi coordinates. So in our SPICE, we have used these variables as a voltage source, and then to solve the differential equation, we have used this capacitor current equation. So it's like I is equal to C dV by dt, and you can get voltage at this capacitor node as an integral of I by C dt. So you can write your LLG differential equation as I, and then you will automatically, your SPICE will automatically solve that differential equation, and the theta and phi will be given by this capacitor voltage. Now, so the transient part, for the transient part, we have used this circuit to implement the LLG differential equation. The thermal part, so like if you don't include the temperature effect, so there are the torques that acts on like uniaxial anisotropy torque, easy plane torque. So at finite temperature, there is another torque applied by the thermal field whose variance is given by this equation. So, and in our SPICE model, we have used the variance of the resistor to generate this thermal noise. So we have included this torque to capture the intrinsic variation of the MTJ. Now so we have done different validations of our model with the published results. So this is one of the validation. So the left plot is the experimental result published in this work. So this is our model results. So basically we have used M and delta as a fitting parameter to match our model, and all the other parameters are fixed. So we use these parameters to fit our model results with this published results. So basically M is used to set the R low resistance, and delta is used to set the TMR of this MTJ, and we get close to 3% of this experimental result. Now we have used this model to study different write energy reduction techniques. So today there was in the grandest talk there is a point that you cannot use JC naught, you cannot decrease JC naught and without touching the thermal stability of MTJ. So the basically write energy of MTJ is high due to the large value of this critical current density JC naught. So we propose that if we use, so JC naught is proportional to the square of MS, the saturation magnetization of the free layer. So if we decrease MS, we will get a reduction in JC naught and we will reduce the write energy, but we'll also reduce the thermal stability. So we propose that if we decrease MS and linearly increase the thickness T of the free layer, we will have the same thermal stability, but because its JC naught is proportional to the T times MS square, we will still get a reduction in JC naught and then reduction in the write energy. So this figure just shows that. So this is basically the write zero in energy comparison for two different MS values, and their thickness are adjusted to get the same thermal stability of retention time of 1 year. And we propose that if manufacturer it's possible to build a low MS free layer ferromagnet, so it will be it should be used for less write energy, to get a less write energy in the STT-RAM. Now, if we want to use STT-RAM in different levels of memory hierarchy, we need to fine tune some design parameters to so that it can be applied to different applications. Like if we want to use STT-RAM for on-chip caches, like L2 cache, L3 cache, we don't need a large retention time. So we can decrease the retention time we can choose different knobs, like we can choose area, we can choose thickness. So in this work, I have chosen thickness of the free layer to decrease the retention time, and as JC naught is proportional to the thickness, so JC naught will also decrease, and we will get a reduction in write energy. So this plot compares the write zero energy for three different retention times of MTJ. Like the top one is for 1 year, middle one is for 1 hour, and the bottom one is for 1 second. So if you want to use STT-RAM, if you want to design STT-RAM for L2 cache, L3 cache, so you don't need a large retention time, and you can decrease using some design knobs and get a reduction in write energy. So that concludes my talk. So, basically, I covered 3 different aspects of my MTJ model. Then how I implemented using behavioral current source and capacitor current equation in SPICE. And then using that model, I propose 2 different techniques to reduce write energy. The low MS one doesn't affect the thermal stability of the MTJ, and the other technique can be used to use STT-RAM for on-chip memories. And I would like to thank Grandis and DARPA for funding this work. And this project is also going on in collaboration with University of Alabama, NIST, and National Research Lab. Thanks.
Questions for the speaker?
I have a question about slide number 15. So my question is, LLG is a damped differential equation, right? So wouldn't you need like a dissipative component, like a resistor also in your circuit to model?
Yeah, the resistor is added in parallel to that.
To the current source?
Yeah.
Okay, thanks.
So this figure just shows how do you like solve the differential equation. So there is a resistor in parallel to this current source.
Any other questions? So I have a question. You talked earlier on there about including the NMOS in your model. I didn't see explicitly where it was included.
So NMOS models are already there. So so this work basically the model that is not right now present. So the MTJ model. So I talked about that.
Okay. Okay, let us thank the speaker. So for our third talk, Manu Awasthi
Yeah.
is talking about handling PCM resistance drift with device, circuit, architecture, and system solutions.
Thank you. So I guess we have had enough of STT-RAM for a while. Let's move on to something a little different. In this talk, I'll be talking about some of the lesser explored phenomenon of phase change memory, which is known as the resistance drift problem. This is a work done in collaboration with IBM TJ Watson Research Center and the Utah Architecture Lab at the University of Utah. So a quick summary of the whole talk is as follows. First of all, the only way phase change memory cells are going to scale in the near future is via multi-level cells. What are multi-level cells? I'll come back to that in a little moment, but just bear with me for a little while. In the recent literature, at least from the architecture side of things have focused on handling problems like hard errors and lifetime issues in phase change memory devices. Resistance drift actually is a pretty unexplored phenomenon from the architecture perspective. So what we believe is that it will become an increasingly significant source of soft errors in phase change memory multi-level cells. To handle such a problem, you would argue for naive DRAM refresh-like techniques, but in the case of phase change memory devices, these refresh-like techniques become exceedingly costly. So what the need of the hour is to explore holistic solutions to encounter drift. So let's move on to the basics of multi-level cells in phase change memory. Phase change memory devices can be programmed into two distinct states, which are namely crystalline and amorphous. The amorphous state has extremely high resistance, while crystalline state has a lower resistance, which actually gives you a band of resistance, which you can split into a number of bins or sets and associate each of these sets with certain bits of information. For example, in what we'd call a 4-level MLC, this whole resistance band is split into 4 bins. Each stores 2 bits of information. Similarly, an 8-level MLC split into 8 bands. Each band stores 3 bits of information. So, first of all, let's see what the problem of resistance drift is and why it is, in fact, a problem. So in this case, let us consider a 4-level MLC. On the x-axis, I have increasing resistance. On the y-axis is time. In this 4-level cell, I have split this available resistance range into 4 different bands, each storing 2 bits of information. Let's concentrate on this particular cell, which was programmed to store a 1-0 value with a programmed resistance of somewhere around here. Let's call it resistance A. As time passes by, what eventually happens if there is inactivity at the cell, that is, the cell is not being read or written, this resistance drifts away and into the next bin, which is the 0-1 bin. So the bin that was supposed to store a 1-0 now stores a 0-1, causing an error. It's worthwhile to note here that all of these bins suffer from the problem of drift, but especially these 2 cells are prone to drift because they can shift into bins and cause errors. This drift is not a problem for this state because, however far away it drifts, it cannot switch into any nearby bin. What are the issues with resistance drift? Let's explore those. So for example, programmed resistance of any cell drifts according to the power law equation as shown here. So for example, if you program a cell with an initial resistance of R0, after time t, the resistance R drift of a particular cell is dependent on the initial programmed resistance R0 and a factor alpha, which is known as the drift coefficient. T, of course, here is time. So in order to actually predict when an error would happen for a particular programmed resistance, since it depends on both the initial resistance and the drift coefficient, the time for a programmed resistance to cause an error is extremely unpredictable. So let's examine why a DRAM-like refresh techniques will not work in such a scenario. So in this case, I again have a 4-level MLC each of these levels has a Gaussian distribution of the initial programmed resistance and the drift coefficient alpha. And this on the y-axis is the number of cells, which is why this is a Gaussian distribution like this. Each of these cells has a mean initial programmed value. So let's consider two different cells. The first cell, which was programmed in the 1-0 state, was programmed with a R0, or the initial programmed value, which was very close to the mean. The second cell was programmed in the 0-1 state and with a initial programmed resistance, which was actually the worst case resistance that you could actually program the cell in. For the sake of arguments, let's also assume that this particular cell had the worst possible alpha it can actually acquire. This cell had, let's say, the mean case alpha. As time passes by, both of these values do drift, but only the one cell programmed in the 0-1 state with the worst case R0 and the worst case alpha causes an error. So if you actually want to resort to a DRAM-like refresh technique, that scrub rate will be dictated by the worst case programmed resistance and the worst case alpha. So how do we get, well, in that case, let's also look at some of the data that we collected from this model that we have assumed. So the worst case 1-0 cell, which is the cell that is most prone to drift. So basically, in the rest of this talk, I'll refer to both these cells as the drift-prone cells. So the worst case 1-0 with the worst case initial programmed resistance can drift to the next bin, which is the 0-0 bin, as less as 6 seconds, even less than that. The 1-0 cell can drift into the next state in as less as 6 seconds. The worst case 0-1 cell can drift into the next state in as little as almost 2 seconds. So the worst case scenario for this, the drift phenomena, looks really scary. So the point to note here is that the drift can be encountered by writing to the cell. So every time you reprogram a cell, you encounter, you negate the effects of drift that had set until now. So in this case, what you can do is you can design a scrub-like mechanism based on existing ECC techniques and get away with it. But in the case of PCM, that's extremely disadvantageous. Why? Because first of all, each write to the PCM cell can take from anywhere from 100 to 1000 nanoseconds. Writing to a 2-bit cell might require as much as 1.6 nanojoules of energy, which, in case you're wondering, is sort of high. And for a 64-bit address space, if you consider PCM devices plugged to the whole big address space, that might require almost 600 refreshes in parallel, which is a lot. So what we need to do is make the refresh reactionary rather than precautionary, happening at every particular time interval. So in order to do that, what we propose is using something called LARD. Well, pardon the nomenclature, but just bear with me. So LARD stands for Light Array Reads for Drift Detection. What we assume here is that we have support for n error detecting, n error correcting, n plus 1 error detecting ECC support. So what we end up doing is at every LARD interval, which is different from a full scrub interval, you read the line, you check for errors. If the number of errors is less than n, and n is again the number of errors that you can actually correct. If the number of errors is less than n, then you don't do anything because you can still correct it. If the number of errors is equal to n, you scrub the line and write the correct value back by correcting with the ECC value. But the problem with such a scheme is that, if between two large cycles, a number of errors could slip through, and you would eventually end up with some unrecoverable errors. So what do you do to encounter that? We propose what we call a headroom edge scheme. So this is nothing but a play on the initial scheme that we had before, but rather than doing a full scrub at the time of detecting n errors, we do it a little early. So we give a little headroom for the errors to not slip through. So what this eventually ends up doing is it increases the frequency of full scrubs, because rather than doing it at every n errors, you're doing it at every n minus h errors. But this also decreases the probability of errors slipping through. What it also gives you is a trade-off between hard and soft errors. For example, if your line had a couple of hard errors, even at that, you could get away with a scrub-like mechanism. So with this basic architecture in place, what more can we do with this to encounter drift? So as we have seen, we have this architectural LARD-like scenario excuse me, in place. We can also build a device level mechanism, a circuit level mechanism, and a system level mechanism on top of that. So for the device level, I'll talk about precise writes and what we'd call guard banding. At the circuit level, we'll try to reduce the overheads of stronger ECC mechanisms by proposing a parity-like scheme, and a system level mechanisms where it takes all of the operating conditions and everything else into account as well. So let's start off with the system level solutions. What eventually ends up happening is dynamic events happen. You have increased activity at the PCM device, your temperature goes up. If your temperature goes up, the rate of drift for a particular cell also goes up. Lifetime is also an issue. Hard errors show up in your lines. So what we need to do is you need to take all these operating conditions into account to decide on a particular LARD and eventual scrub rate. So for example, what you can do is you can start with a really low LARD rate. That is, you have a large amount of time between two LARD cycles. But as and when you detect, say, increased temperatures, or you detect hard errors creeping up into your memory lines in the system, you sort of double or triple or increase your refresh rate or a LARD rate by a certain amount. So I did talk about how stronger ECC has larger overheads with both storage and circuit level complexities. So let's say if you wanted to have support for detecting 9 errors and correcting 8 errors, you would you have approximately a 25% overhead as compared to a, say, SecDed scheme. So what we propose is using something like circuit based on parity-like scheme. For example, what do you do in here? So in this scheme, every time you write to a particular line, you count the number of drift-prone states. You have an additional flag bit in which if the number of drift-prone states is odd, you write a 0, and if the number of drift-prone states is even, well, or the other way around. If the number of drift-prone states is even, you write a 0, and if the number of drift-prone states is odd, you write a 1. You compute this parity bit at every large cycle, compare it with the stored flag value, and when there is a mismatch between the computed value and the stored value, you make a full-fledged scrub. So what this essentially does is reduces the need for ECC read compare at every LARD operation. Basically, you have to do the full ECC correction and read only when you have a flag mismatch. And these, as I referred to before, are the two drift-prone states. So in one of the device-level solutions, we propose something what we term as a precise write. So let's consider the case of a particular cell with the Gaussian distribution assumed for both initial program resistance and alpha values. In this case, I just consider the initial program resistance. So what ends up happening in the worst case write in this particular distribution of initial program resistance is your worst case write has only this amount of margin to drift and hence cause an error. Remember, as before, if the drift resistance value crosses into the next bin is when what we call as an error. So what you need to do is make your writes more precise. That is, you decrease the amount of resistance range that your cell can be programmed into. In this case, even your worst case write has a larger state or larger distance to cover before it actually causes an error. But this comes at a cost. So for a more precise write, you'd have to carry out iterations of read and write and then write again until you get a particular write value. So first of all, it causes it costs more energy, and second of all, it hurts your lifetime because you are writing again and again to reach a particular value. The second device level solution that we propose is called non-uniform banding. So as before, we have the resistance range on the x-axis. It's divided into 4 different states for a 4-level MLC. Each is stored with each is associated with 2 bits of information. What happens here is that the 2 drift-prone states have almost equal amount of distance to cover as far as the problem of drift goes. So what we do is we take away some of the resistance from the not so drift-prone states and give it to the states that are actually drift-prone. So in the end, the writes to these drift-prone states have a little more wiggle room, and hence the probability of an error happening goes down. So again, to summarize, in this particular work, we propose 4 different kinds of solutions to encounter drift at the architecture, at the device, at the circuit, and at the system level. So, excuse me. At the architecture level, we proposed headroom schemes with trade-off error rates with lifetime. At the device level, we proposed precise writes and guard banding, which trade off between error rate and write energy. At the circuit level, we have solutions which try to reduce the overheads of ECC with a parity-based scheme. And at the system level, we combine all of these into one big umbrella and account for varying operating conditions. So to summarize, what we believe is that resistance drift is a big problem in the current MLCs, and it's going to exacerbate as MLCs scale to have more and more states. Naive solutions based on ECC support are going to be extremely costly with increased write energies and decreased lifetimes. So what we need to explore are holistic solutions as we sort of proposed in this paper. And because this is still a work in progress, what we could achieve with all these solutions in place was a 39% reduction in energy, 4 times less errors, and 102 times increase in lifetime as compared to a baseline with full refresh in place. Thank you. And I'll take any questions if there are any.
Are there any questions?
Yep.
You mentioned that one of your slides, you mentioned that the mean for the drift for certain states is like a 10 to the 8th or 10 to the 24th power in terms of seconds. But
yes,
the worst bit can move within 1 or a few seconds.
Right.
If that were the case, then you increase this lifetime by 100 times seems not enough.
I agree. Yes, but I mean, for the time being, with the proposed solutions, that was the best we can do.
Will this problem become a showstopper for PCM to get adopted in your mind?
I don't know that for a fact right now, but I mean, and I'm not exactly the best person to answer that question. I mean, this has to do more with the materials. So from what I have heard and read so far is that the new materials coming in might be able to encounter this problem at sort of the material level itself. But even if that happens, we still would need some sort of mechanisms in place so as to handle that as and when PCM scales. So it might not be a showstopper right now, but it might be in the future.
Okay, thanks.
Yeah.
Any other questions? Right here?
Thank you. I have 2 short questions.
Sure.
The first one is, seems like cell level drifting is a serious problem for PCM. Mm-hmm. So therefore, how practical, how many levels can we store in PCMs? Can you comment on that?
Comment on how many levels can we scale to?
Basically, yeah, for a multi-level cell, what's the maximum number?
I would not like to say anything which will cause me trouble later in the future, but what I can say is we did experiments with both 4 and 8 level cells, And we found that the problem was existent for both as of now with the current data that's out there. So I mean, we didn't make any exorbitant assumptions that, okay, this is what it's going to be like. We just developed our models based on the data that is out there. And even based on that, we saw that it is still a problem. So if it's a problem in 4 and 8 level cells, it's going to be definitely a bigger problem in 16 and 32 level cells.
Okay, thanks. Second short question is, when the cells drift, can you comment on how uniformly they drift?
So as I mentioned, okay, let me just go back to that slide. So all of the cells do drift. So in this case, as I mentioned, all of the cells do drift, but this rate of drift goes on increasing as you move towards a higher percentage of amorphous state. But depending on your rate of drift, the error-causing states are the 2 middle ones. Does that sort of answer your question? But I mean, just to state as a fact, the rate of drift increases as you move towards a higher percentage of amorphous.
Is it the same for the different cells? Is the rate of drifting the same for the different cells?
That also depends on a number of factors. I mean, there could be process variations that effects that could come into place. But for one given cell, if you look at the cell in isolation, the rate of drift for a particular state increases as you increase the percentage of amorphous content.
Okay, yeah. Let's move on now.
Thank you.
Thank you. Thank you. Next, we have probabilistic programming of STT MTJ clusters with Wencheng Wu. Mm-hmm.
It has been a long day, so thanks for hanging on there. And this is the last presentation, and we can go to the dinner. And I'm Wencheng Wu from Qualcomm, and I would like to share some of our unexpected findings we had during our spin logic research and development work. And also, thanks for today's lots of presentations on spin torque transfer magnetic tunneling junction technologies. So I don't need to introduce STT-MTJ technology. We can just move on to our core materials. So, and the spin torque transfer magnetic tunneling junction memories has been the technology has matured that non-volatile memories of practical use can be made out of it. But probably due to the influence from the design paradigm from traditional memories such as SRAM and the DRAM, and the STT-MTJ RAM has been designed based on the principle that the memory element switching is deterministic, but in reality, the switching of STT-MTJ is probabilistic in nature. So I think you can see from these figures, depends on how your programming pulse applied, and the switching is not always 100%. And so that's why we choose one region to do read and another region to do write. And so that's because under the influence of deterministic programming, so in the conventional STT-MTJ MRAM, the design is to have the write or programming of the STT-MRAM to happen only during at the region which is switching is approximate deterministic programming. And we will show you to this requirement actually makes the STT-MTJ MRAM programming takes more power and also consume more time. And it also possesses unnecessary bit error rate, which is expensive to reduce. if we, based on our MRAM design, to use deterministic switching. So this region used for deterministic switching. We will show you this is not the right region. And so instead of being taxed by the requirement for deterministic switching, and we can we need to exploit the probability switching property of STT-MTJ. And by doing that, we can reduce programming power and also programming time. We can also have a bit error rate dynamically tunable to adapt to all practical use. And also we can improve STT-MTJ MRAM to have a density beyond the 1 bit per transistor. That means essentially that's a multi-level cell. And to accomplish probability programming, we will need to have a special programming algorithm and also memory structure. The MTJ clusters serve as memory elements for probability programming. And in each MTJ cluster, we can have multiple MTJs connected in various topology. And the MTJs can have the same size or different size. And so when we have different size, the size can be 1, 2, 4, so that each MTJ can be distinguishable. And the top topology B and C are what we put in our test chip, which was taped out last year, October. And the programming algorithm starts by setting the right value, and then we will sense the cluster to see if the cluster has reached the right value. And if it's not, we're going to select the appropriate programming pulse to apply to the cluster. This process iterates until the right value has been reached by the cluster, or the iteration has a timeout. And the timeout actually determines the bit error rates and can be achieved by the probabilistic programming. If we use in theory, if we use a bit timeout infinity, then the bit error rate could be 0. And also, if we will have using special circuitry, this sensing of the cluster and the application of a programming pulse can be done at the same time. So, so in our analysis, we don't consider the sensing as a cost. So here we do we show you an example of probabilistic programming in action. We use in this example we use Monte Carlo simulated 1 million STT-MTJ clusters, and each cluster comprises 3 identical STT-MTJs, and the programming pulse is selected such that the switching probability of a single STT-MTJ, PMTJ, is 55.6 upon application of a single selected programming pulse. And all 1 million STT-MTJ clusters start from the state S1, which has only 1 out of 3 composing STT-MTJs in anti-parallel magnetization state. And the targeted state is S2. You can see here S2, which has 2 out of the total 3 STT-MTJ in anti-parallel magnetized state. And we will apply programming pulses to drive appropriate programming pulses with the appropriate polarity. And so to drive from S1 to S2, that's our targeted state. We'll see after 23, within 23 iterations, or 1 million clusters reach the desired state. And and with the average iteration, it's 2.23. So in this example, we realized the bit error rate is 0, and had we used the timeout 23 instead of we give it unlimited time to program, we can use a timeout 23. We can reach a bit error rate at 7.8 times 10 to the minus 9. For conventional deterministic programming to reach the same bit error rate, 7.8 times 10 to the 9, then we would require the switching probability of STT-MTJ to be very small, not very small, very close to 1. And that requires the corresponding programming pulse to be 23 times as long as the ones we used here. And that extends to 7 times in power and 10 times in programming delay if we write 2 bits at a time for deterministic programming, just like apple to apple. Because here we program once. This one cluster actually it's 2 bit because it's a multi-level cell. So it's worth noting that case 1 and for probabilistic programming and case 2 for deterministic programming, they all have the same bit error rate, the same maximum programming delay, which is 23 pulses long. But they have 7 times in programming power and 10 times in programming delay. And so now we want to find out, we just showed you a case of programming, probabilistic programming can save time and power. And we want to find out how much power and time can be saved in general. And so to do that, we need to come up with analytical equations for an average programming iteration, average programming time. So we have derived the equations for the single STT MTJ using probabilistic programming, and for the average number of iterations for programming and the average programming time. And we notice that if we would apply the switching probability to be small, infinitely small, we can reach minimum average programming time. This p tau is the switching probability for STT MTJ with a children pulse and pulse amplitude, but the pulse width is tau. When this one is tends to infinitely small, and this number will be infinitely large, but we can reach a minimum average programming time. And luckily, we don't need to know the detailed physics behind the p tau to find out exactly what this average minimum programming time is, and for a given STT MTJ fabrication process. We can read this one out from the probability switching graph here. So once we have, we can get this graph from the chip. We fabricate it. We can take a measurement of the switching probability with respect to the switching time, and we can read out this number from at the point when the switching probability is 63.2, and that's the time. That's the minimum programming time we can reach with the probability switching. That's in our case. In this case, is 28 nanoseconds, which is much smaller than the one used for deterministic switching, 80 nanoseconds. And also for the multi-level cell case, we have we also derived the equations for the average number of iterations and the average programming time. And so this diagram shows how the average programming iterations varies as a function of the STT MTJ switching probability. And we notice there is optimum STT MTJ switching probability, the one we used, let's see, for a single STT MTJ switching probability. And once we use that one, that programming iteration can be minimized. So we want to find out what is this optimum STT MTJ switching probability. So, and actually this turned out to be a very complex optimization problem, because we want to find out the STT MTJ switching probability that minimize the average programming iteration that average over all clusters and over all cluster states. That's a very complex problem. But luckily, we found a solution which is the probability can minimize iteration is 1 over square root of n, and this is the minimum programming iteration at that time is given by this equation. It turns out this figure shows our answers to this complex problem really fares well. And now we are able to find out how much exactly how much power and time can be saved with probabilistic programming versus deterministic programming. we define epsilon as the time required to program an STT-MTJ using deterministic programming, and versus the time using probabilistic programming to program the same STT-MTJ. It turned out we have a very simple relationship between this ratio to the bit error rate from the deterministic programming. Notice when we're programming the same STT-MTJ with the probabilistic programming, we assume the bit error rate is 0, but with this one we have with the deterministic programming, the bit error rate is always finite. And so for a few typical bit error rates from the deterministic programming, we have a corresponding epsilon, which means the power saving we can achieve by using probabilistic programming. We can see for for the 10 to the minus 4 to 5, this what's a not typical Zohr bit error rate from the STT device. We can have up to around about 10 times programming delay and programming power saving. And keep in mind this epsilon is represents the theoretical limit of probabilistic programming saving can be accomplished for programming a single STT-MTJ. And the bit error rate from the probabilistic programming is 0. And had we use the timeout to make this bit error rate for probabilistic programming the same as a deterministic programming here, then this epsilon would be even larger. And for multi-level cell programming, we define the overhead as because once we have the STT-MTJ, it's essentially a multi-level cell, and we define the programming overhead as the time required to program the m-bit multi-level cell versus the time required to program m single STT-MTJs probabilistically. So this is also probabilistic programming. This is also probabilistic programming. This is just m single and STT-MTJs. Here is just one cluster. And we got this equation and with a few typical numbers listed in this table. We can see for the 3 bits, which is actually the 8 levels, multi-level cell, the overhead is pretty small, which can be easily absorbed by the efficiency gain from the probabilistic programming shown in this table. And for the multi-level cell greater than like 30 or above, and it's not economical anymore. We need to resort to some other means to reduce overhead. This slide is just to illustrate how the STT-MTJ clusters can be fabricated. And for one case, we can connect the STT-MTJs in one STT-MTJ cluster through conventional wiring and through via and conventional wiring. So using this method, we don't need to have a new STT-MTJ fabrication process other than the ones used for STT-RAM. If we are willing to develop a new process, we can abut the STT-MTJs or stacking them. By doing this, we can have an extremely high density STT-MTJ clusters made out of it, and we can have the STT-RAM with a multi-level cell and have extremely high density. So here we're showing two application examples of using STT-MTJ clusters. MRAM made out of multi-level MRAM made out of STT-MTJ clusters can have the density can easily have a density much higher than 1 bit per, actually 3 bit per cell and per transistor. And also because MTJ itself does not take up the silicon footprint, so the density it's extremely high in comparison to flash. And in the meantime, MRAM made out of STT-MTJ can run much faster and also consume much less power with probabilistic programming. And also, STT-MTJ clusters can be used to make analog ECC for the benefit of speed and area. And just like what we show here. And Another thing is that due to the very nature of probability switching of the STT-MTJs, and the STT-MTJ clusters naturally fit the role of synapses in neural network. So to summarize, and instead of to be limited by the conventional memory design paradigm to use deterministic switching, we should instead use, try to approach switching probability to be 100%. We should actually use switching probability to be as small as possible. And that sounds a little paradoxical. But the fact is that the smaller you use, the less likely you're going to overprogram. Then you can save power and the time. And in the case we want to do multi-level cell programming, we can use the switching probability of 1 over square root of n to minimize the programming iteration. And we should always use a beta error rate based timeout to limit the maximum programming delay to be no larger than the corresponding deterministic programming while having the same beta error rate. So with that said, I'm open to take questions. Thank you so much. Thank you. So say it loud.
Several MTJs if you have several MTJs in a cluster, and one of them switches in a series of MTJs, then that's going to dramatically alter the switching probability of the other ones in the cluster, isn't it? So I'm wondering if practically, how does this work?
Can you repeat the question? So because I think before you had a... Oh yeah, this is just a preliminary theoretical study, and it's very preliminary, and we just show we have a new way to do a better programming. And so in this simulation, they all have the same switching probability, and to simplify the simulation, all the MTJs are the same. Just like I said, there's another way we can have a different kind of MTJ, so we can distinguish them which MTJ is switched. But this one, because they are identical, we only count how many is switched. So by this at a level. Suppose you have 5 MTJs in a cluster. Yes. And 2 of them in lowest state, 3 of them in highest state. So the voltage across MTJ will be different for each MTJ, right? Right. So the switching probability will also be different. Not switching probability, because it depends how you put them in. Depends how you put them in a topology. See here, like if we put them in parallel connection. I'm sorry. In series, it's right. In series, this one when you apply it, and then when I flip, then I agree there's an impact. So that's what we used. We have both structure in our test chip. We wanted to find out what exactly going on. But in our case, in this study, we just assume they have the same programming switching probability. But in reality, they may not have the same switching probability. Then that's a second order approximation. We want to study that. And another thing, we can always to change the programming pulse. Pulse means the width or the height to adapt to the new programming probability.
Are there any other questions?
So if we go to the previous slide, I noticed that you show 2 ways to change P to AP. One is high pulse, but less wide. The other one is shorter pulse, but it's wider. And in practice, which one works better?
That one, we didn't look into that detail. For this study, we only assume we have a certain programming pulse can give us a certain switching probability, because we only go to the switching probability. So then we select the programming path to reach that probability. So this whole study basically we want to find out what's the optimum switching probability. Then to reach that probability, there is another question: how do we do it with what kind of path, how long, and that's another thing.
Okay, can we say that this iterative program method you described, can we say that it's similar to the iterative program method for flash memory?
It is on the iterative side, it's the same, but the principle is different. Because we want to see, in our case, we want to have the probabilities as we can show here. So that's a principle. We don't want to have we don't want to have a probability switching switching probability to close to 1. Actually, we have some. That's what the optimal switching probability we want to use, and this is for multi-level cell. And actually, for single cell, and this is supposed to be as small as possible. So this is to minimize the number of iterations. If we so minimize, if we go to these slides. So in these slides, to minimize the programming time, actually, you want to use as small as possible. So it sounds a little bit paradoxical, but the fact is that the smaller the use, and the less likely you're going to overprogram. Because a lot of times, the cell has switched, but you still continue to apply your programming pulse, which consumes more power and time.
To my understanding, that you want to use this optimum programming pulse because you want to reduce the programming time and power. So from your simulation, can you tell that in reality, in your simulation, how much reduction of power and time that you can achieve?
Yeah, that's what I give you an example here. So for this example, the power can save it 7 times, the time can save it 10 times. And also this let's see. In this table, it shows the power and the time saved is depends on how much bit error rate you want to accomplish. For bit rate, you want means in comparison to the deterministic programming. If deterministic programming only wants to accomplish the bit error rate 10 to the minus 5, then you're going to take, instead of using deterministic programming, you use probabilistic programming as what we put up here. The power and the time savings, the factor is 11 times. And also, this is also once you use the timeout, as what's saying here, the maximum delay from probabilistic programming is no larger than deterministic programming.
Okay, thank you.